Hi, everybody. My name is Trepka, and was a student in the Tau group at the Roland Institute at Harvard, and I conducted most of the work I'm presenting today as an undergraduate, and I'm currently a graduate student at UCSF. So today I'm going to be talking to you about rare earth oxide nanomaterials and their applications in magnetic scanning probe microscopy. So just as a brief refresher, magnetic scanning probe microscopy is a technique that relies on sort of scanning a magnet over a sample or a sample over a magnet. So several examples include MFM, susceptibility force microscopy, and MRFM, which is the focus of our lab. So the setup of magnetic force microscopy is the cantilever handle is run with a magnet over a magnetic sample, and depending on the magnetic force exerted by the sample, changes the oscillations of the handle to give an idea of the quantitative magnetic feedback. So there's two primary modalities for setting this up. The first is having the sensor on the chip, so having a magnet under the sample and sort of letting the sample oscillate back and forth. The second modality is having the sensor on the cantilever tip. So this is having a magnet on the cantilever and placing the sample underneath of it. So next, I'm going to discuss rare earth oxides for magnetic scanning probe microscopy. So there's two basic types of magnetism. You'll notice I excluded diamagnetism. So the first is ferromagnetism, and this is a type of magnetism where after the spins are aligned, it takes some extra energy to unalign them, versus paramagnetism, where once the spins are aligned, if no magnetic field is applied, they relax back into a totally free state. And you'll notice that for ferromagnetism and paramagnetism, I've displayed the graphs of magnetism versus the applied field for two representative samples. So an ideal material for a magnetic scanning probe application is both robust to fabrication. It has a high magnetization or magnetic saturation, MS. It has a low hysteresis or a low remnant magnetization and coercive field. And it has a long linear range or H-lin. So then the result of the combination of these conditions is a fast imaging time and a high signal to noise ratio. Rare earth oxides are, in theory, ideal for this purpose. They're paramagnetic, which means they have no remnant magnetization and no coercive field. They have a high theoretical bulk saturation magnetization, so above 2 Tesla. They have a resultingly long linear range, and they're theoretically robust to oxidation as they are already oxides and in the most stable crystal lattice structure. So the first thing I'm going to discuss is the sensor on chip modality. So we have grown through physical vapor deposition a holmium oxide thin film that displays superior magnetism to many current materials. At cryogenic temperatures, so this graph is presented for 4 Kelvin, the magnetic saturation is above 2.5 Tesla, which exceeds that of the current best ferromagnets such as iron or iron cobalt, and it has no remnants or coercivity, which is desirable for scanning over a sample and for the quantitativeness of a measurement. And it also has this extremely long linear range, which gives us a long dynamic range of sensing. Beyond these superior magnetic properties, we also have several desirable other properties. So the film forms an atomically tight interface on the sapphire substrate. Putting this film in 49% hydrofluoric acid or just blasting it with oxygen plasma results in completely unchanged magnetic properties. So looking at this graph, you might not be able to see the second line because it completely overlaps with the first. And this could be manipulated onto the substrate for scanning using FIB. The second modality I'm going to discuss today is the sensor on tip modality. So for this application, we have investigated the magnetic properties of commercial rare earth oxide nanoparticles, where the rare earths investigated were gadolinium, dysprosium, holmium, and erbium, most with around 20 nanometer radii. So once again, the magnetism of these materials is at cryogenic temperatures superior to many current magnets, ferromagnets, and beyond that, they are paramagnetic, so they have zero remnant magnetization and they have zero coercive field, which makes this lack of hysteresis makes them ideal for sort of the scanning, probe, and quantitative applications where we need to rapidly switch back and forth, but we don't want any hysteresis losses. And once again, you see that the linear field or the linear range is above 2 Tesla. So one proposed manipulation strategy for actually putting these tiny nanoparticles onto the tips of cantilevers for scanning is to use glancing angle deposition of nanowire handles. So this is just a technique, a physical technique where a source material, say in this picture, germanium, is evaporated onto the nanoparticles, and self-shadowing sort of results in this nanowire growth, which is depicted in the figure. One other interesting feature of these commercial rare earth oxide nanoparticles is that they appear to have magnetic dead layers. So if you remember from prior slides, the theoretical magnetization of these rare earth nanoparticles should be above 2 Tesla, but here we observe only above 1.3 Tesla and none quite reaching that 2 Tesla mark. And this is actually consistent with prior work, which suggests the emergence of 1 to 10 nanometer dead layers in iron oxides and in other complex metal oxide thin films. So we decided to model the response of the magnets that you see in the colorful graph on the left using 2 distinct magnetic subpopulations, one that we consider to have a sub-ideal magnetization and one that has the ideal magnetization for that rare earth oxide particle. And we find through this modeling that the magnetic responses we observed are actually consistent with 2 to 11 nanometer dead layers on the surface of these rare earth oxide nanoparticles. So these dead layers are magnetically weaker, magnetically inert in comparison to the theoretical ideal magnetization of rare earth ions. So you might be wondering, well, actually, how do these materials compare for the purpose of magnetic scanning probe applications? And I would like to introduce the concept of linearity of magnetic energy density, or ELIN. So this is defined as the energy density that can be quadratically stored into a material under the drive of an external field. This naturally captures both the magnetic sensitivity and linearity of a material and is defined by the following equation. So looking at a plot with achievable magnetization at a 7 Tesla applied field on the y-axis and a linearity of magnetic energy density on the x-axis, ideal magnetic material for scanning probe applications would be in the top right. And we indeed find that these commercial nanoparticles, as well as this novel holmium oxide thin film that our group has created, all appear sort of on the top right, having higher linearity of magnetic energy density than any other recorded material so far, and competitive saturation magnetization or achievable magnetization with extremely good ferromagnetic materials such as bulk iron or dysprosium nanopillars. So in conclusion, we have synthesized a holmium oxide thin film with thickness below 100 nanometers that has a record high linearity of magnetic energy density, a magnetic saturation exceeding 2 Tesla, 0 hysteresis, and a robustness to extreme conditions such as HF etching and oxygen plasma. We've also discovered 2 distinct magnetic populations in rare earth oxide nanoparticles. And sort of synthesizing all of this together, we believe that rare earth oxide nanomaterials have superior magnetic properties for scanning probe microscopy applications. And I would like to acknowledge the Ye Tao, my PI, as well as the other Tao Lab members and our collaborators, and also all of our funding sources. Thank you.